It's not like that. Viterbo gets a ton of race because it's like a festival, so like any some kind of religious holiday or anything like that, you get another race. But that isn't so
And we don't have to follow the rules of like for high schools. I don't know if college is the same way, but like.
All right, so here we are. We've got the video going again. So we start with the next sections,
Yeah. So
which have to do with the other kinds of stuff we have going on. So we're going to page 634. So I'm not sure if I can do that here or not. Nope. So I have to go back here. And then go here. And then go to 634. There, okay, so what we're talking about here is a person who is pitching a baseball game. And we have then this list of percentages that they normally do, or that we expect them to do. And then we take a look and say, okay, well, that's not what happened in this recent game. So, did he deviate from his usual pitch count? In other words, did he pitch the number of pitches in the categories like we expected him to, or did he not? Okay, that's the question that we're asking. Right? So, what kind of a thing are we going to do with this? How are we going to resolve this issue? What are we going to say? We're going to do a hypothesis test. Yes, we are. Jackie, can you tell me what kind of hypothesis test we're going to do? We are doing number 4. Yes, we are. Page 634. No. Okay, Danielle Koch, can you tell me? Nope. Donna, can you tell me?
Goodness of fit.
We are doing goodness of fit. Okay. Goodness of fit. All right. So, Taylor, can you tell me null and alternative hypotheses?
The null hypothesis would be that he didn't deviate from his pitch count.
Okay, he didn't deviate. And the alternative?
Would be that
He did deviate. If we were to use more technical terms, we would say the null hypothesis would be that the proportions match the given list. And then what would be the alternative? Emily Grenier, can you tell me? At least one proportion, and specifically population proportion. At least one proportion is different from the given set of proportions.
Do you want the answer to be about the problem or just that?
I would prefer the answer be about the problem. Well, you could say he didn't deviate from his previous proportions, and he did deviate at least one way from his proportions. But this would be okay, right? To put it in the statement of the problem itself is okay to do. Right? So, Allie, what's next? We need to find the critical value, okay? So, Humphrey, can you tell me how to find the critical value in this situation? No, we don't. Natasha, can you tell me where to look for the critical value here? It's the chi-squared table, and where on the chi-squared table am I going to look? That's correct. Degrees of freedom would be 3 because 4 minus 1. So we're going to look under alpha of 0.05. What do we find when we look there? 7.815. So Lisa Peterson, can you tell me what that looks like in terms of a graph?
I'm still writing down what you're all this.
Okay. So I want to know what the graph looks like for this. Haley, can you tell me what the graph looks like for this? Okay, so we're going to start here on the left side with 0, and then we're going to go out here to 7.815, and we're going to fill in that part out there. That's our rejection. Okay, that's what the graph looks like. Okay. So, Evie, what's next? I want the test value. What do I need to do in order to get the test value for goodness of fit, Evie? Okay. Lishabelle, can you tell me what I need to do to get test value for goodness of fit? Okay, I will need to do that. How do I get my expected values in this situation? I multiply what by n? Okay. Haley, can you tell me what I multiply by n? No. I want to multiply that by something. What do I do? Okay, which percentages? Okay, so the ones that I'm given for my given list, I'm going to multiply those by the total number of pitches, which I n. So I'm taking n times p, and the p here are from my given list. So I have the list of percentages, and I'm going to be multiplying them by the total number of pitches. How many total pitches do I have here? 111. So I'm going to be taking each one of those percentages times 111. So what's 0.62 times 111? Did you say 68.82?
Yeah.
Okay. So that would be my first expected value. How many times would I need to do this, Haley? 4 times. I have 4 categories. So that's what I would get. So here are my expected values. I've actually done them for you so that you can see them, but you need to know where they come from. So then I would put those into my chi-squared formula, and I would get my chi-squared values, which I would then add together, and then that would represent my test value. So by looking at these numbers right here, Eric, can you tell me what my test value is?
8.3184.
Okay, so we'll call it 8.32. That'll be fine. Here's my critical value. My test value is equal to 8.32. All right. When you say stuff, I don't know what you're referring to.
So you just did 0.62 times 111 gave you 68.82.
That's correct. That was my expected value for that first category.
Correct. And to find the chi-squared number, you would do 56 minus 68.82 divided by 68.82.
I would have it squared on top. 56 minus 68.82 squared divided by 68.82.
And that equals what?
That's the chi-squared value for that first category, which is 2.3881. Okay, Natasha, does that answer your question?
Hold on before you move on.
Yeah, I will. Okay, hang on just a second. Natasha, I don't want you to figure out all four of those numbers right now.
No, I'm just writing them down.
Okay.
I don't know where they're coming from.
Okay, that's fine. I just wanted to make sure that you weren't trying to do all the calculations, because I don't expect you to do that. Okay. Okay. Right? So this is what you're going to see on the test, a list of numbers. You'll need to interpret them. You will not need to calculate them. Right? So here we are. Okay. So, Eric, can you tell me what to do next?
We're going to reject it. The null hypothesis. I
Yes.
know.
Yes, we are. Phineas and Ferb, I didn't get to see the whole thing. It was really pretty good.
What's that?
Phineas and Ferb, it's a series, television series. Very good. Yes, yes it is. So test value 8.32, so you reject
Null hypothesis.
the null hypothesis. Okay, so what does that mean, Eric?
We're going to reject it.
No.
No, I'm just kidding. I'm just kidding. There's enough evidence to prove the alternative hypothesis.
What you should have said was there's enough evidence to prove it. And then I would have said, no.
It's on it. It's being thrown around today.
Okay, so Kelly, what does that mean? You nonverbals are telling me you're not sure exactly what that means.
That's
Okay, Amanda, can you tell me what this means?
I'm not sure.
Okay, before I go on, Kelly and Amanda, I'm going to give you another 10 seconds to think. There is enough evidence to prove the alternative hypothesis.
He did deviate.
Kelly?
He did.
He did deviate. Okay, that's the alternative hypothesis. Yes, he did deviate. All right. All right. Ms. Peterson.
So for the critical value, you have chi-squared is greater than 7.815.
I do.
Wouldn't you just say equal to that?
That's technically the rejection region.
Oh, okay.
The critical value is 7.815. The rejection region is chi-squared greater. So, Kelly, did he follow his normal pattern in throwing pitches?
No.
Eric?
No.
No, he deviated. He did not do the same thing he normally does. He did something different. Okay? This is the conclusion of the chi-squared test. Something is different in at least one of these categories. He did not follow the pattern that he normally does. Not just a random fluctuation. There's a distinct difference here in what he did. Okay? We don't know what that is, but that's not good enough for us. We do want to know what it is. So we're going to look at confidence intervals. Here are the confidence intervals. All right. You will be given these numbers. You will not be expected to find them, although technically you should be able to because you know how to do confidence intervals, supposedly. But here they are.
What's your question?
The question is, what conclusions can we draw from these confidence intervals? Unfortunately, you're not correct because when we're using confidence intervals, we're supposed to get a specific value and a specific direction for that deviation.
Are we comparing the chi-squared numbers to those?
We are not doing anything with chi-squared when we're talking about confidence intervals.
Is this where like if a lower is higher than an upper?
No, it's not. What are we talking about? We're talking about a given list of percentages.
Plus percentages there.
So are the percentages the same as what we expected them to be, or are they different? That is the question that we need to answer. We're not doing anything with chi-squared. We are not comparing the confidence intervals with each other. We are comparing each confidence interval with the percent that we expected it to be.
Is the slider and the change up are within the expected range?
Since the slider and the change up are within the expected range, we cannot say that there's a difference there. Okay. What can we say? And the difficulty here is that you have to recognize that the confidence interval is the actual measurement. The thing we expected was something that came from somewhere else. But what we're asking the question is my actual measurement in the confidence interval different from what I expected it to be? Okay, so Amber, what can you tell me? Not sure. Okay. Danielle in the front, can you tell? All right.
So are we comparing the given or the expected numbers?
Okay, what are we comparing? We are comparing proportions now. Okay, we're not comparing these expected numbers, which are frequencies. We are comparing these, yes, to the confidence intervals. No. Okay. What are we comparing? We are asking the question, is the thing that I measured different from what I expected it to be? This is what I expected it to be. These are my given list of proportions. These are the proportions that I thought it was going to be. I'm asking the question, are my measurements different from these proportions? What direction are they different? Which one is lower?
Curveball is lower and fastball is higher, which is what.
Is curveball right here lower than what I expected it to be? No.
No, but the PI is lower than yours.
But that's not the question.
So then it's higher than yours.
What is higher?
The curve.
The curveball proportion is higher than I expected it to be.
So fastball is lower than
Fastball is lower. So the question that's being asked right here is, what did the pitcher do different than expected?
He threw more curveballs than he did fastballs.
He threw more curveballs than expected, and he threw fewer fastballs than expected. That's the answer to the question. What happened in this game? The pitcher threw more curveballs than what were expected and fewer fastballs than what were expected. That was the decision that was made in the game. Now, as you have to realize, the catcher and other members of the team are also involved in the process. But this was what happened. So when we say the curveball is higher, we're talking about the confidence interval being higher than what's given. So the answer to the question is, where is the confidence interval in relation to where I expected it to be? It's higher for the curveball, lower for the fastball. That's the answer to the question. Generally speaking, very few people get this right, even after doing it half a dozen times, which we've already done it maybe 3 or 4. So you need to be relatively careful about how you do this problem. If you haven't written this down yet, it'd be a good idea for you to write down exactly what are the steps in doing confidence intervals for goodness of fit. You look at the confidence interval and you compare it to the given proportion. If the confidence interval is higher, then that proportion is higher than expected. If the confidence interval is lower, then it's lower than expected. And you're comparing the confidence interval to the given set of proportions. For the slider and the changeup, we can't say anything because it could be lower, it could be higher. We don't know. We can't say. But we are able to say that there is a real significant difference in the case of the fastball and of the curve. All right, that's goodness of fit. What happens next? The next thing is Number 10 on that assignment. Cardiovascular procedures. So now we're looking at what kind of things happen for treatment. So Amber, can you tell me what the general name of this thing is that we're doing here?
Test of independence.
Test of independence. Danielle, up here in the front, can you tell me what the null and alternative hypotheses are?
Categories do not affect proportions.
Okay,
For null and alternative categories do affect proportions.
okay, categories do not affect proportions. And the alternative is that categories do affect proportions. And there are other words that we use for this. Allie, can you tell me what the other words are? Independent and dependent. So in this situation, we're asking the question, is it true that the types of treatment are related to whether someone's a man or a woman? Does that affect the type of treatment that they receive? Okay. So, null alternative hypotheses. Amanda, what's next? Critical value. So, Emily Grenier, can you tell me where the critical value is going to be? It is on table G.
And then degrees, rows -1.
Okay, degrees of freedom is rows -1 times columns -1. What's that going to be here, Emily? How many columns are there? How many rows are there? 2. 2 minus 1 times 3 minus 1 would be 1 times 2. 2 degrees of freedom. Kelly, you got that number? 2 degrees of freedom? Okay. Okay. It's looking the same as the other one. All right. Donna, what's next?
What did we just find the critical value?
Yes, we did.
What do we find the test value?
Okay, we need the test value. So what do we need in order to get the test value? Oh, you told me wrong. What's it supposed to be?
4.605.
Alpha is 0.05 and your degrees of freedom are 2. Oh, alpha is 10. Oh, slip one in on me. I'm sorry, what was that number?
4.605.
4.605 alpha. Okay. Thank you. Okay.
Test value.
No, this is the critical value. Critical value comes from the table with degrees of freedom. So, Donna, what do we need for the test value? How do we go about making that happen?
We make a chart with all the numbers on it.
Okay. And what do we need to put on our chart?
We have 2 rows, men and women.
Okay.
A column for coronary artery stent.
Yep.
1 for artery bypass.
Okay.
The pacemaker.
All right.
We want a total for each row and we want a total for each column.
Okay. Well, where did I put it? I guess I didn't put it anywhere. I thought I had. 2017. So,
I thought you had it last week or something, didn't you?
yeah.
But you can just do it on a computer, but we have to do it all on paper.
No. Okay. No calculations. I'll give you all the numbers. Right?
Wait, you're giving us all the numbers on this stuff?
Yes.
Oh, dang.
How many times have I said this? I don't know. How many times have I said this? A lot of times. A lot of times I've said this. A lot of times I've said this. No. Okay. All right. So we'll change it and make it here. So, men and women, right? Oops. 425, 227. $320, 123. This one. $198, 219. Okay. Yeah. So there they are, or here they are. Either way. So it's just numbers? Yeah, it is. Okay. Da, da, da. Okay. Huh. Well, I don't know what that is. Okay. So we find the expected values by doing what?
Rows total times column total divided by.
Okay. How many times do we need to do that, Natasha? 6 times. Okay, so we find all 6 of those expected values. Then we calculate the chi-squared for each one of those. And we end up with a total chi-squared of 59.95.
Okay, I have a question.
Okay.
So, after you got all the expected values, you then, you do the other part then 6 times too, right?
Yep. Will you have to do that on the test? No, you won't.
So what number is, sorry,
This is the test value.
right?
When we find the,
Where's that, how's that gonna be located on information?
it's a great question. So here's the chi-squared. Here are the numbers for all 6 of them. This is. Test value, chi-squared is equal to 59.9. Okay, so Evie, what happens next? I have a test value. I have a critical value. This Peterson, can you tell me what happens next?
You have like this null hypothesis because test value is in the reduction region.
That's correct. Okay, so as a Peterson, what does that mean?
If there's enough evidence to prove the alternative hypothesis.
What does that mean?
That categories do affect proportions.
Okay, and then specifically for this situation, what does that mean?
Gender effects. I don't know what exactly said. Gender effects procedures.
Okay, so there's some kind of an effect between the gender of the patient and the procedure that they experience. That's all that we can say when we're doing test of independence. We cannot say specifically in this situation using chi-squared what the difference is. However, the fact that we just have men versus women here, we could express those as percentages, and then we could go through and do something similar to goodness of fit with percentages to be able to say, is there an actual difference here between these things? And let's see, G3 compared to G14. So it looks like if you just compare the expected with the observed, that women have a substantially lower number of bypasses and a substantially higher number of pacemakers. So women get pacemakers at a higher rate than men, even though there were more men in the study than there were women. The actual number of pacemakers was higher for the women. Now, I'm not a doctor, so I really don't know what's going on and if that's a big deal or a good or a bad thing. I don't know any of that, but I can at least tell you that there's something going on here and it's different. All right, so that was test of independence. What could possibly happen even further than that? Well, not just p-value, but page 637, number 23. Prices of athletic shoes. Okay. So I have a list of numbers, these prices for these athletic shoes, and I have different categories. So the question that I need to ask is, what procedure am I talking about, and what am I trying to prove? ANOVA. No, that's not what I'm trying to prove. What are we trying to prove with ANOVA? Taylor, can you tell me what I'm trying to prove with ANOVA?
You're comparing averages with different categories.
I'm comparing averages in different categories. Okay. So ANOVA, I do need to understand the variation in order to do ANOVA. But what I'm actually comparing are averages in different categories. Okay. So, Jackie, can you tell me what's the null hypothesis for this?
What are we doing?
We're doing number 23 on page 637. It's the last problem.
So, mu1 equals mu2 equals mu3.
Okay, that's correct. The null hypothesis for ANOVA is that the population means are equal. Jackie, what's the alternative?
At least one average is different.
Okay, at least one mu or population mean is different. Okay. So this is ANOVA. We begin by looking at simply the first section here. What conclusions do we draw from what I have up here on the screen? Danielle Koch, can you tell me? Okay. Haley, can you tell me what I can do with this information up on the screen? Okay.
We're just supposed to look at a few values.
You are correct so far. Jackie?
Oh, you can't do anything, you can't draw a conclusion just off of the sample data.
That's correct. We cannot draw any conclusions from this because this is just sample data. So we can't draw any conclusions. Okay? That's the correct answer. Are these averages different? Jackie? Yes, they are. But we don't know right now if they are substantially different. Even though they might seem to be, we don't know yet if the differences are significant or not. They could just be random fluctuations. We don't know. We have to do ANOVA in order to see if the fluctuations or the differences are significant and not just fluctuations. So we go down here to ANOVA, and here's ANOVA. Okay. Bless you. Abby, can you tell me what I need to do with this ANOVA table? I do. What do I do when I look at people? Okay, that's correct. So, Haley, what happens here? Okay, what does that mean?
At least one unit is different.
Okay. So that's telling us that there is some kind of a significant difference in what for this particular problem? What are we measuring? There is a significant difference in what? Eric, can you tell me?
The average price of shoes.
Okay, for
women, children, and men.
okay, so there's some difference here in the population mean, okay, between men, women, and children's shoes. We cannot say that any one type of shoe by itself, when I go out and buy shoes, I can't say that my shoes are going to be different than somebody else's. But what I can say is on average, there is a difference between these three categories in terms of the population mean or the average price of the shoes. Okay? All I know from ANOVA is that there is some difference, but that's not good enough. We need confidence intervals to actually know what that difference would be. So we go down here and we say, hey, what is the difference? Kelly, can you tell me what the difference is based on what we have on the screen here.
Men's are higher priced.
Men's are higher priced, okay? Men's are higher priced compared to women's and compared to children. Okay? This is where we're actually comparing the confidence intervals with each other. Previously, we were comparing confidence intervals with a given set of percentages. That's not what's happening here. Here we're comparing population means with each other. The men's average is higher than the other two. How do I know that? Because the upper of this is below the lower of that. Okay, so as high as this goes, it's still going to be below this one. That's how I know that this mean is lower than that. All right, that's it.
So what happens if we bomb this test? What kind of like time do we have to retake it?
Unfortunately, retakes are not generally available for test number 4, since after all, it's the last one.
When will the test be?
Grades are due on Monday at 4 o'clock. So that's most likely when they will be done. They might be done earlier, considering I only have one class. I should be able to get it done before.
I feel like I voted so hard every time.